Now here's an example of our circadian rhythm. And so if we think of, the day part and then the night part, we can see that there are various things that change at different times of the day. So let's pick it up and start here at, say, 4:30 in the morning. So at 4:30 in the morning, we have our lowest body temperature. Our metabolism is at its lowest. A couple hours later, we can see that at 6:45, oh, we see an increase in blood pressure. The body's picking up again, right? Waking up again, more physiological processes are going to start kicking in. Now, at 7:30, secretion of melatonin stops. And so that's going to help us become more alert. Again, our body's kicking in. Bowel movements will be likely at about 8:30. Testosterone secretion is highest at 9. Highest alertness at about 10 a.m. Best coordination at 2:30 p.m. and so on. Greatest cardiovascular efficiency and muscle strength at 5 p.m. Highest actual blood pressures at 6:30. Highest body temperatures at 7. Melatonin secretion is going to start right here at 9 p.m. As the night wears on, we're going to start getting sleepy, of course. Our physiological processes are going to start being suppressed, allowing us to sleep. And so that's an example of the circadian cycle. Our circadian cycle, again, that's just our sleep-wake cycle. Sleep stages that occur during sleep are an example of what's called an ultradian cycle. An ultradian cycle repeats more than once a day, and so we'll see in a moment that we repeat these different cycles of sleep while we're sleeping. The menstrual cycle in females is an example of an infradian cycle. This is a cycle that repeats less often than once a day, in this case once a month. Now let's take a look at what actually happens during sleep. We're going to be looking at EEG data. So this is an electroencephalogram that is looking at what is happening in terms of our brain activity as we transition from being awake to the different stages of sleep. So here we have a sample EEG to take a look at. Here we have the overall EEG. We'll see in lab that an EEG is a recording made of brain activity using electrodes that are just placed on the scalp. So this is the combined activity of many neurons, right? And so the EEG is just the overall activity of a large number of neurons. We can break down the different components of an EEG by just filtering out these different types of waves. And one type of wave is called an alpha wave. Another is called a beta wave. We just have them here in alphabetical order. So alpha, beta, delta, and theta. So let's take a look at the two awake types of waves, and that would be alpha and beta. Beta is the one that's the most active, so think of busy beta. And we can see that brain activity is characterized by waves that repeat 13 to 30 times per second. So here we get 13 to 30 hertz for beta waves. In other words, 13 to 30 of these individual peaks in a second of time. So let's take a look here at our timeline. Here we have 2 seconds of time. And so if I was to divide up 1 second, it would be from here to here. So that would be 1 second of time. And if we were to count up the number of peaks here in this 1 second of time, we would have a number that would be between 13 and 30. Beta waves are seen when a person is actively working on something. So if you're looking at something, then you're probably going to see a large amount of beta activity in the visual cortex, for example. If you close your eyes you stop processing visual information. And at this point, then you should see an increase in alpha wave activity. Alpha waves are a little bit slower, and so we get only 8 to 13 of them per second. And so if we were to count these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 or so is what we get here. And so we're certainly within this 8 to 13 per second. And so again, these waves are characterized, or they're defined by the number of cycles per second. So alpha, yes, the person is awake, but relaxed. In other words, not actively processing anything. So this would be eyes closed in the case of recording from the visual cortex. Beta is awake and busy. And so, for example, that would be eyes open if recording in the visual cortex. Theta and delta waves are seen during sleep. We'll start off with theta waves. These are seen in a light sleep. And we can see that there is a characteristic frequency of 4 to 8 cycles per second. And so if we count them here, we see 1, 2, 3, 4, 5, right? So certainly within that 4 to 8 per second. Delta waves are the slowest. We'll see half to 4 cycles per second in delta waves. So these are indicative of extremely little brain activity. And as a person sleeps, we start seeing more delta waves. Are we still going to see an overall greater amount of brain activity? Absolutely. But the percentage of their overall EEG that is made up of delta waves will be higher during deep sleep. So delta is characteristic of slow wave sleep. And you can see that they have a high amplitude. So a big up and down. Why? Because there's just fewer neurons firing. And so we're really just picking up the activity of a much smaller number of neurons firing. And in general, when neurons are firing, they're not synchronized, they're not firing together, they're kind of all firing at different times. And so some are going to be at the peak of their action potential, others are going to be more negative. And so it's impossible when there are many neurons firing usually to get this big up and down. But if you only have a small number of neurons firing, then it's possible for them to sort of synchronize a little bit more easily, and they just happen to maybe all fire at the same time, and so you'll get this bigger up and down pattern. And that's what you're seeing during delta waves. Again, it's just an indication that there's not as much brain activity going on. And remember, when your person is asleep, their EEG will not look like this. Their EEG will certainly show much more activity. But if you look at how much delta wave activity they have in their sleep, it'll be much higher during slow wave sleep than at any other time. You really won't see it at any other time. Now let's take a look at how we transition from one stage to another while we're sleeping. Here we start off awake. We briefly go into stage 1, the lightest stage of sleep. Then we go into stage 2, again very briefly. We go into stage 3, and then stage 4. While we're in stages 3 and 4, we're, remember, in that slow wave sleep. Early in the night, notice that we kind of stay in 3 and 4 stage sleep for quite a while during that first hour and a half. And then our brain activity picks up. We don't ever go back into stage 1. Instead, we enter REM sleep, rapid eye movement sleep. And then we can see that that's designated here in this little block period. Spend a short amount of time in REM sleep early in the night, and more time during stages 3 and 4, slow wave sleep, during those first 4 hours of the night. Now, as we continue to sleep, as the night progresses, notice what happens to the length of time spent in REM sleep. It goes from being very brief to much, much longer, right? In addition, the amount of time spent in slow wave sleep that was so big early in the night is now a much smaller portion of our sleep time. So we spend more time in slow wave sleep early in the night than later, and more time in REM sleep later in the night or after more hours of sleep than initially.